Assalamu alaikum students, and welcome to our new lecture. We are now moving, after discussing all those things that we did before midterm and then a few weeks after midterm. We are now moving to hydraulic machinery. The hydraulic machinery has two basic components that are included in our scheme of studies. One is turbine and another is pump. We are going to start from turbine, and then we'll move on to the pump. There are two lectures on turbine in our scheme of studies, the HEC scheme of studies. So we are going to spend 2 weeks on turbines and then around 2 weeks on the pumps. So let's start the first lecture on the turbine. We are also, let's see what we are going to discuss in this lecture. We'll basically first of all look at the basic difference between the two, the pumps and turbines. Then we'll be moving to the turbines and discussing different parts of it, different types of it. We'll see how momentum equation is applied to turbine. Perhaps the momentum equation would be looked into the next lecture, but at least we'll look at the efficiencies today, how to calculate efficiency, and we'll also try to solve some numericals. There would be other numericals that would be given to you. I'll upload them later on, but at least initially we should go through the concepts that are included in this part. So let's look at the sections that you are going to follow. These are the sections of chapter number 16 that we are following, starting from 16.1 through 16.9. Only 16.5 section can be neglected, and then the other sections of this book are also important, but they are not part of our scheme of study, so we are not going to look into them in detail, but it's up to you. If you want to look at them, there are certain very interesting sections also. For example, different kinds of turbines that have been installed around the world, the size of them and the different properties of them. So it would be nice if you can also go through other sections if you have interest in them. But obviously the sections that have been mentioned here are the ones which are included in our scheme of studies, and in which we will be considering our exam. So first go through all these sections. I'll be going through all the things that are mentioned in those sections in this presentation, and perhaps the next week's presentation. Also look at the solved examples that are there. We'll also solve a very simple numerical here in this lecture, and then I'll upload some more later on. So let us look at the hydraulic machinery. A very typical example of turbines and pumps combined are in jet engines. Jet engines are getting complex with time, and more sophisticated, more efficient. But jet engines are interesting in a sense that both the important hydraulic machinery, that is the pumps and turbines, are installed in one particular section. And because they have to work for a very long time in a very tough condition, for example, at quite high altitude where the density of air, the velocity of air, and other properties are quite different, so they have to work at their optimum level. So these are important hydraulic machineries. The fluid can be air or water or anything else, but mostly they are working under the same principles, whether it is air or water. Let us look at the difference between the basic difference between the two. Pumps, as you already know, and we discussed it very briefly previously when we were looking at Bernoulli equations and the total energy available in the fluid, and we said that when we are getting the energy from water or calculating energy at a particular point in a fluid, then we are looking at the pressure head, at the velocity head, at the geodetic head, and then there are also head losses in that equation. And if you remember, we also said that there is a part where either we would be taking energy from the fluid or we will be introducing energy to the fluid. And those devices which do these things are pumps and turbines. Pumps are energy absorbing devices. They absorb the energy, and they transfer that energy to the fluid. through different things. One of them is rotating shaft. And this increase in fluid energy is basically felt as the increase in pressure of the fluid. So when we are introducing energy into the fluid through the pump, we are basically increasing the pressure of the fluid. Turbines, on the other hand, are energy producing devices. We extract energy from the fluid or from whether it is water or air, and we transfer ideally all of that energy uh, through the rotating shaft to certain sections, and we transfer it or we change it to the mechanical energy. And basically the fluid that is then all the energy when it is taken away from the fluid, the loss of energy is in form of loss of pressure when we are using it for turbines. So basically, you see, for example, let's say this is our pump. The flow of water or air is in this direction. So we are putting certain, and this flow has already particular energy in it. What pump does is that through this shaft, we are introducing energy into that fluid. The flow goes out from another end, and there is obviously certain energy associated with the flow which is going out of the pump. And the pump, as we said, we are introducing energy into the pump, so that outgoing energy is greater than the incoming energy from the fluid. So you see our arrow is in this direction, which means that we are supplying energy to that fluid through this rotating shaft. On the other hand, turbine, rest of the nomenclature is the same. The only difference is that you will see that now this arrow is in this direction, which basically means that we are taking energy out of that fluid system, again through this rotating shaft. And this outgoing energy is now less than incoming energy. So you see this energy or the fluid that is going out of the turbine has lower energy than at the time when it was entering the turbine, because this loss of energy is transformed through this shaft to some other devices which can be seen later on. So this is the basic difference between the two. Again, both are energy devices. One is absorbing energy, another is producing energy. And as we said, the purpose of the pump is to add energy to the fluid. And that energy is resulting in a form of increase in pressure. Now, you should understand that once we add to the pressure of the fluid, that pressure is not necessarily translated into the speed of the fluid. So it's not necessary, but basically what we are doing is that we are increasing the pressure of the fluid, which we sometimes observe as that pressure is resulting into the high velocity of fluid, but basically it is the pressure which has been increased. The turbines extract energy from the fluid, as we said earlier, and this is then basically decrease of the fluid pressure. The pressure has been taken out of that water. If we take a control volume around any device, whether it's a pump or a turbine, control volume, as we discussed in the very initial part of the lecture, is basically a frame of reference for us for which to which we are looking at, and we are observing what is happening around the body of this control volume, how much momentum or fluid is entering that control volume, how much is going out, and we look at the properties. So basically, if you remember our initial equation, the mass of conservation of energy, we said that mass flow rate out of the pump must be equal to the mass flow rate into the pump, which basically means that the difference that is being there is the difference of the pressure. You see, the mass flow rate is the same, but the pressure has been increased. It is also important to note that these dias can be different. I mean, in this picture they are shown to be equal, but it is possible that the system which is entering that control volume is entering through a dia which is larger, and when it is going out of the control volume, it can be smaller. So this should be taken care of. You might remember this diagram. We looked at it in the initial part of our Bernoulli equation when we were calculating the hydraulic rate line and total energy line. As we said, with the pump we are basically taking electrical and mechanical energy, and we are taking and we are converting that energy to the fluid energy. In turbines, as we said earlier, the energy that is already in the fluid is taken and it is converted into electrical or mechanical energy. You also remember this total energy line or hydraulic rate line, and we said that, for example, let's say we are transporting water from this reservoir to that one, then because this reservoir is at a higher level, we need to have certain energy for the water to be able to be transported from this one to that one, and that energy is introduced into the fluid. This fluid energy is increased through the pump by electrical or mechanical energy. So we install that thing here. Basically, if water is flowing into this pipeline to this pipe, we would be having losses in a system, frictional losses. The pump would increase the pressure of the fluid. The pressure would increase the total head. The total head would be able to transport water to the higher reservoir. Similarly, if the picture is reversed and we need water from this upper reservoir to lower reservoir, then obviously it can travel by itself through gravity because this one is at the lower location. But sometimes we also need more energy into that system so that we can take energy out of the water and use it for some useful purposes. You see, if you remember or if you might have seen the Ghazi-Barota project, where we are taking water from the Indus River, and then we are putting this water again in the Indus River somewhere downstream. There is a lot of available head to us, and using that head, we have Pakistan has developed this Ghazi-Barota project where just by gravity flow we are taking energy out of the water in the Ghazi-Barota hydropower project, and we are converting that energy into electrical energy. There is no loss of water. We are just taking water out from the river at one location. Using the head, we are transporting that fluid through a power channel to certain turbines. Those turbines, all the energy is taken out from the water, and then downstream we are again throwing the same water into the Indus River, which then flows downwards to the Sindh, then finally to the sea. So we use that energy, we take this energy out from the water, running our turbines and creating electricity. There are other types of turbo machinery. For example, the pumps that we are using, we are also introducing energy into that system, whether it is the air pump which we use for our bicycles, or whether they are the water pumps, the previously used water pumps. We use the up and down motion of the piston here, and we extract water from the groundwater. So turbines have been used for centuries to convert freely available mechanical energy from rivers and wind into some other useful form of mechanical work, which is then converted into any other form of energy. The important thing is looking at the different parts of the turbines. The rotating part of the pump is called impeller, and we'll discuss that later on. But the rotating part of the hydro turbine is called the runner. So this term should be used. This is that part of the turbine which is rotating. If we are using water as a fluid, then we call these things or these machines as hydraulic turbines or hydro turbines. And if obviously we are using air, then we will be calling them the wind turbines. Um, the word windmill should technically be applied only when the mechanical energy output is used to grind grain, um, or to do some pumping water or generate electricity. Uh, the turbo machines that convert energy from the steam into mechanical energy of rotating shafts are then called the steam turbine. So you see we have these different, the structure is the same, the rotating shaft or the runner is the same, but if we are using water as a fluid, then they are called hydro turbines. If we are using wind, they are called wind turbines. And if we are using steam, then they would be called steam turbines. We'll see probably a couple of pictures of steam turbines when, for example, if you, let's say we have nuclear power plant, either through nuclear energy or from coal, we try to create steam, and then that steam is forced into turbines, which rotates the turbines, and we create the electricity out of it. We have already this Chashma project, and we have also other nuclear power plants which use these energy through steam turbines. Fine, let's move forward. And look at the difference between the efficiencies of the two hydraulic machines, the pumps and turbines. As a You see, in general, all the hydraulic machinery which produce energy, they have higher efficiency than the hydraulic machinery which absorbs energy. Fine. So this is one basically a thumb rule, that energy producing turbines or energy producing hydraulic machines have higher efficiency than do the energy absorbing machines or machinery. For example, turbines, and specifically hydro turbines, they have almost 95% of efficiency. And at the best, if we can, the best efficiency that we can get from the energy absorbing devices, for example, pumps, are around 90%. The major reasons of this are the following. The one is because of the speeds. The pumps usually have the rotating shaft in the pump is usually rotating at a higher speed than the turbines. So as we have studied earlier in our laminar and turbulent flows, the because of these higher rotational speeds, we have higher losses. So there are more shear stresses, and there are also frictional losses in the system, which somehow reduces the efficiency in pumps. So the pump is an energy absorbing device, and some of the efficiency is reduced because of these higher rotating equipment inside the pump. The second reason is that the conversion of kinetic energy into flow energy, they usually have inherently higher losses. So this is in general the observation that has been made. Secondly, turbines, and especially the hydro turbines, and we'll see some of the turbines, some pictures of the turbines in this presentation. They are much larger than the pumps, which then make the viscous losses less important. You see, we have during the in the laminar and the turbulent flow, we studied that there is, if the water is going through the hydraulic through the pipe, there would always be a viscous sublayer, and this width of viscous sublayer diminishes with increase in the pipe size. If you remember, we discussed these things, and because of this reduction in viscous sublayer, the viscous losses would be less. So because turbines are much larger, which makes those viscosity related losses less important, and because of these things there is less loss in the turbine as compared to the pump. Fine. Um, Basically, we uh, classify the turbines into two broader categories. One is the positive displacement turbines, and then there would be some other turbines in that, some other classification in that, and then there are dynamic turbines. And the basic difference between them is that these positive displacement turbines are usually used for measuring the flow rates. Fine, but these are small turbines. We'll see an example maybe in a couple of slides. Um, they are only used for the flow rate measurement. Um, on the other hand, the dynamic turbines, they can be smaller, but they can be also very huge, and they are usually used for the power production. They can be used, these huge machines can also be used for flow measurement, but these dynamic turbines are usually used for the power production. On the other hand, positive displacement turbines are smaller in size and they are normally only used for the flow measurement. The positive displacement turbines, they are usually smaller devices, as we said earlier, and they are used for measuring the flow rate. The most common example of the water meter or the water turbines of positive displacement types are the smaller turbines which are usually installed not in our country but in some other, mostly the developed countries. They have these kinds of water meters installed in at homes, and there is a flow into that system. Um, uh, Many commercial water meters use a rotating disc that wobbles and spins as the water flow through the meter. So there is water entering to the system, this rotating disc that revolves, spins, and the disc has a sphere in its center with appropriate linkages that transfer the eccentric spinning motion of the rotating disc into rotating of the shaft. And then the volume of the fluid that passes through the device for each 360-degree rotation of the shaft is known precisely. So we know that what volume would make this rotating disc revolve 360 degree. So we count these rotations, and these rotations are then converted to the total volume of water. When water is flowing at a moderate speed, from let's say a spigot, you can you usually can hear a very small sound coming out from them. But because we do not have these spinning devices installed at home, you might not have seen it. But in mostly, as I said earlier, mostly developed countries, they have water meters, and those water meters are of this type, and you will see very clearly that when the water is flowing through them, there is the meter, just like our electricity meters and our gas meters. They have these numbers on it, and you can find out how much water you are using. Dynamic turbines, as I said earlier, can be used for flow measurement, but they are not generally used for flow measurement. They are used for power generator. They use the larger elevation change, and they use that energy uh, to convert it into the hydraulic electricity or hydroelectricity. There are then two basic types of dynamic turbines. One is called impulse turbines, another one is reaction turbine. The impulse turbine, they only work if they have very higher head available to them. When the head is high, for example, in dams, in power projects, you would always install an impulse turbine because they do require higher heads. It's not necessary that the volumetric flow rate is high. Even with small volumetric flow rate or small discharge, they can work, but the head should be larger so that they can convert that head into that rotating energy. Reaction turbines, on the other hand, are also larger in size. They are also used for electricity production. And their advantage is that they can also work at smaller heads. For example, if you are installing a turbine in some hilly areas, in for example in Kalam or Bahrain, because the head, or let's say the gradient there, is very steep, you cannot, for example, install a very large or you can not make a very big dam there. What you can do is that you can use the higher flow rates or of the water which is flowing in the river very fast. You can use that higher flow rates and make a very small dam, for example 2 meters or 3 meters of head, and these turbines would work there as well. So the head can be smaller, but the volumetric flow rate should be larger um, in those kinds of reaction turbines. The examples here are shown here, this A and B. This one is related to the anemometer. Meteorologists use a 3-cup anemometer to measure wind speed. So this is basically a wind speed measuring device. Experimental fluid mechanics researchers usually use small turbines of various shapes to measure air speed or water speed, and this basically converts this rotating speed into the speed of the air or water, whatever the case may be, and then this is displaced. Another novel application of a dynamic turbine is shown here in this small aircraft. This is a NASA aircraft, and they have the researchers have mounted turbines at the wingtips. So here you can see at the wingtip you see these small turbines, and these small turbines, because of the air movement, they rotate and they are converted this rotation is converted into electricity, and that electricity is then used for on-board electricity that is required for display and for other smaller things. So these are uh, typical examples of dynamic turbines. So they are not necessarily should be very large, but the two types should be remembered. There is impulse turbine and a reaction turbine. Okay, so the impulse turbines, as we said, these are the larger turbines which require higher heads. The volumetric flow rates can be smaller, but the heads should be smaller. In an impulse turbine, the fluid is sent through a nozzle so that most of its available mechanical energy is converted into kinetic energy. Um, this high-speed jet then impinges or it goes into the bucket-shaped vanes. So these are different vanes of these turbines, and they are shaped like buckets. So they go into these bucket-shaped vanes and transfer energy to the turbine shaft, and the turbine shaft is installed here. The modern and most efficient type of impulse turbine, they were invented back in 1878, in fact, by Pelton, and that's why they are also called Pelton wheel turbines. Um, and the buckets of the Pelton wheel are designed in such a way that it splits the flow in half and turn the flow nearly 180 degrees around. So you see there is this jet nozzle. The water is going out with a certain velocity. This Vj is the velocity of jet. It hits that bucket, these vanes, and these vanes are in a shape of bucket. So the water hits them. The water is in itself almost rotated on 180 degrees back. So this is the velocity of water in this direction when it is entering the vane or the bucket, and when it is going out into this direction. So we are splitting the water into these two parts. A portion of the outermost part of each bucket is cut out so that the majority of the jet can pass through the bucket that is not aligned with the jet. That is this bucket n plus 1. So you see part of that would be hitting this bucket, which would rotate, and then the half of the jet is hitting the next incoming bucket, which is then n plus 1. And in so doing, we have this high rotational speed of this turbine, which is then converted to this shaft, and this shaft is then going to the generators, and we'll see how this thing is connected to the generator. And the important thing to look at here is the flow velocities. In the previous lecture, where if you remember, we discussed the velocity of jet and impact of jet, and there were impact of jet on a stationary instrument and impact of jet on a moving instrument. So the relative velocities would be important here. You see, when water is hitting or when water is going out of the nozzle in this direction, this bucket is also moving with a particular velocity in this direction. So water is in this direction, this bucket is moving in this direction. So we have to calculate what is the absolute velocity of this jet and what is the relative velocity when it is hitting that bucket. And these two would be then used to calculate the total amount of energy that can be extracted from the water. These are the typical examples of the impulse turbine. You see here there is the view of a Pelton wheel turbine, and this is then a Pelton wheel which is in operation. So basically you are looking from the bottom. This Pelton wheel is moving in this direction, the jet is moving in this direction, and Pelton wheel is rotating into this direction. So this is in this anti-clockwise. So for example, you are looking at from the bottom and you see that it is moving in this direction, then moving up and going back in this direction again. You see the water jet is hitting this bucket or this vane, and also part of the jet is hitting that the next incoming bucket. Okay, another one was the reaction turbines. So the dynamic turbine is, if you remember, had two types, the impulse and the reaction turbines. And we said that in reaction turbines, it is not necessary that the head is very high, but the volumetric flow rate should be higher. And looking at this design, you would realize that yes, it is important that we have higher volumetric rate so that the vanes or the blades are run in an efficient way. This basically consists of fixed guide vanes called the stay vanes. So for example, these are the fixed vanes or the fixed directing vanes, which basically directs water to enter into this main chamber. So they are called the stay vane. Then we have adjustable guide vanes called the wicket gates. These smaller ones are called wicket gates. And finally, the rotating blades, which are called runnel blades, which are in the extreme inner part of this turbine. The flow enters tangentially at higher pressure because we have higher flow rate. So we ensure that the water enter, for example, at the higher pressure. This is turned towards the runner by these stay vanes. For example, the water is coming into this from this direction. These stay vanes are making the water enter into this system and then hitting the main blades. So the flow enters tangentially at higher pressure. They are turned towards the runner by the stay vanes, and it moves along the spiral casing and then passes through the wicket gates with a large tangential velocity component. You see the momentum that we studied earlier. Momentum is exchanged between the fluid and the runner as the runner rotates, and there is this large pressure drop. Unlike the impulse turbine, the water completely fills the casing of the reaction turbine. So we have this complete casing is filled with water. And this is the reason that a reaction turbine generally produces more power than an impulse turbine of the same diameter, um, net head, and the volume flow rate. It is important to know that the angle of the wicket gates is adjustable, so that the volumetric flow rate can be controlled through the runner. So this is the basic difference between the reaction turbines and the impulse turbines. You also should note that in a good design, the number of wicket gates does not share a common denominator with the number of runner blades. Otherwise, there will be this severe vibration which is caused by a simultaneous impingement of two or more wicket gate wakes onto the leading edges of the runner blade. And this is important because you see, we have to have a certain kind of similarity between the stay vanes and the wicket gate, so that the water that is entering here is not misdirected and it doesn't um, um, create any kind of problems for the runner blades inside the reaction turbine. Okay, so these reaction turbines are then also can be divided further into two other kinds of turbines, namely the Francis turbine and the Kaplan turbine. You can go through these definitions which are mentioned here. They are basically more or less the same, but the difference is in the way how the water or any other fluid is entering the turbines and exiting the turbines. For example, here you see that we have these different kinds of entry and exit points. For example, if you look at this reaction turbine, water is entering in the wicket gates in this direction, and then it is hitting the stay vane almost axially, and that's why they are called Francis radial flow. You see, this is the rotating shaft, so the shaft is rotating like this. Its axis, the rotating axis, is this one, and this water is entering in the radial direction. In another type, the water would be entering the system and it would be turned before it hits these blades or the vanes of the turbine. So they are turned to a certain with a certain degree in this direction, and this degree is somewhere between the radial and the axial direction. So this would be your axial direction, this would be your radial direction, and this one is somewhere between radial and axial direction. So the water is hitting the vanes or the runner of the turbine in this direction, and then they are basically called Francis mixed flow turbines. So this B is the Francis mixed flow turbine. This one is more or less the same thing, except that there is no band in here. You see, we have this band structure here, which is not present in this section. The flow direction is more or less the same. And if we transform the direction of the flow in almost in the axial direction, so you see the water has almost transformed or turned towards 90 degree towards this blade, and then this blade is moving. So this is then called the propeller axial flow because the flow is now in the axial direction. So these are different kinds of reaction turbines based on how we are directing the flow towards the runner of the turbines. This is one typical example of a Francis turbine, and this is a Francis radial flow turbine. So you see the water would be entering in this direction radial to the axis of the rotation. So this would be your axis of rotation, and this is in radial direction. The water is entering into this direction. There are almost 17 runner blades of a particular diameter, and they you can see the size of it. It revolves around 180 revolutions per minute and produces an electricity of 119 megawatts. And interesting to see is that they are using a high head of 105 meters. So this is quite high head of 105 meters with a volumetric flow rate of 127 cubic meter per second. Um, this is now then the mixed flow turbine. You see, we said earlier that we have this mixed flow turbine. So this one, where the water is entering in here and it is turned to a certain degree, but this degree is not axial, it is not radial, it is somewhere in between. And that is basically this kind of structure. So the water is entering into this and then it is transformed into this in this direction, and this is then basically the runner blades on the lower side. Again, these are almost 17 runner blades with a particular diameter, 100 revolutions per minute, and the 194 megawatt of power is produced within a volumetric flow rate of 375 cubic meter per second. So you see the difference between the two. In the previous case, we had 105 meters of head, but the flow rate was comparatively lower. Here we have smaller head for 54.9, but the volumetric flow rate is larger. This is a Francis mixed flow turbine. And there are also some other turbines, and you can go through them yourself. Important for us to look into is the total available head for the turbine to convert this head energy into electrical energy. Let's say we have a dam, we have a penstock which is transporting water from this from the reservoir to the turbine. We need to find out what is the total head available to the turbine. The basic thing is the same. We calculate the head just before the water hits the turbine and then just after the water goes out of the turbine. We calculate the head at these two locations. The difference between two is the net head which is available for this turbine to work under. Now the total gross head is the difference between the tailwater level and the upstream reservoir water level. So the difference between the tailwater and the headwater would be your gross head. But our net head is the head which is available for the turbine to transform this head into electrical energy by transferring its rotating energy through a shaft to the generator, is the head which it can use just before and after the turbine. And this is our net head. Obviously, if we include the datum here, then this from the datum to the top of our reservoir water level would be our complete head of the system. So ideal power production is calculated through this equation: rho g, volumetric flow rate, discharge, and the head. So if you have the total discharge and you have the head, then you can calculate how much power would be produced by simply multiplying these two values with g and the density of water. Gross head, as we said, is the difference between the total head available minus the tailwater at this end, or the difference between these two, the tailwater and the headwater in the reservoir. This is our net head for a hydraulic turbine. Efficiency is then calculated, as you might have already know. Efficiency is then the output divided by the input. It's always the same: output divided by the input. Output in case of turbines is the rotational speed of the shaft, and input is the water horsepower, or how much water, how much power is there in the water. This is our input. So you see, our input is related with the incoming water, the head, volumetric flow rate, and rho g. Output is our rotational speed of the shaft, which is in then brake horsepower units. So we'll see a small example here as well. So efficiency is always output by input. For a pump, it is then vice versa. You see the difference between the two. In case of pump, the output is the output of the energy of the fluid. So we have rho g h q here, and in case of turbine, this is our input, because this is the water that is going and creating the power. So this would be then our input, and this would be output. So they are reciprocal to each other. Fine, we looked into this. This is a very simple example, a simple numerical on hydroelectric power plant. So the example is that we have a hydroelectric power plant that is being designed. The gross head from the reservoir to the tail race is 1065 feet. So this part is also called the tail race. This one is also called the tail race. You see the tail race, it is written here. So this head is given to us. The gross head from the reservoir to the tail race is 1065 feet. The volumetric flow rate of water through each turbine is also given. Perhaps there are multiple turbines, so for each turbine you have been given the total water that is going through each turbine, which is 203,000 gallons per minute. And we have been told that there are 12 parallel turbines, and the efficiency of each turbine is 95.2%. There are also other mechanical energy losses from the penstock or any other installations that are inside the pipe, and they combinedly they are reducing the output by 3.5%. So for example, if you have entry losses, and then there are frictional losses, and then there are penstock losses, so all of them combined reduces the output by 3.5%. This is also given to us. The efficiency of a generator is 94.5%, and we have to estimate the electrical power production from this plant. So very simple question. We just have to calculate the input and output, and we have to use that particular formula that we just looked into. So first of all, we need to calculate how much ideally this water can produce electricity. And as we said, rho g multiplied by the discharge multiplied by the gross head, which is given to us. So we put all the values. 62.3 is the density of the water at this particular temperature. G 32.2 feet per second or 9.8 meter per second, whatever the case is. Volumetric flow rate is given to us, and the head is also given to us, 1065. We multiply all these things and we get the values. We do some conversions from megawatt to watts and minutes per second, 60 seconds per minute. We do all these conversion and we get on answer in megawatts, the total. So this is now the ideal output of this water from this particular system. But we have already been told that there are certain efficiencies, and these efficiencies have to be taken into consideration. So what we do is that we multiply or we reduce this megawatt with these inefficiencies. So this 40.70 of megawatts is multiplied by the efficiency of the turbine, which is 0.9, efficiency of the generator, which is 94.5, and then also the efficiency of the turbine, which is 95.2. So we are multiplying all these efficiencies with it, including the losses. So the losses were 3.5%. So 1 minus 0.035 are the rest of the losses. So we multiply all these things and we get the electrical output from this system. This was the ideal system, but when we included all the inefficiencies, this is the output from each of the turbine. And then we have been told that there are 12 turbines in parallel, so we multiply 12 with each one of the efficiency and we get the total megawatts of megawatt of energy that is produced from this system. So you see from 1065 feet, and in this case we have a lot of water available, 203,000 gallons per minute for each turbine. So you have almost 12 turbines installed and there are, let's say, 12 penstocks coming to each one of the turbine, hitting this turbine with this much of water. So obviously we are getting an energy which is in excess of 400 megawatts. Fine. We also said that we also have then other kinds of turbines depending upon what kind of fluid it is catering for. So there are gas and steam turbines as well. You go through it from the slides and also from the internet, because in our book, the book that we are following, there is no mention of gas and steam turbines, but it is important to look into them as well. They are not part of your scheme of studies, but it is an interesting topic in itself. So just go through them. The gas and steam turbines, they work the same. They have the same nozzles, the blades, the buckets, each and everything is the same. The only thing that is different is the fluid. So just go through the text that is mentioned here in the slides. Similarly, we have the wind turbines. Also, this is not part of your scheme of studies, but because we are going through a time period where renewable energy is very important for us, so wind turbines are also working in the same way as other turbines. The only difference is that they are run by the wind. They are usually costlier than the hydro turbines because of the fact that wind is not always blowing in certain areas. You might install a lot of windmills, but it would only run when there is wind in there. So it is important to first of all find an ideal place where there is enough wind so that we can install the wind turbines. And because they are quite costly, so ultimately per unit charge or the per unit produced by the wind turbine is costlier than the water unit. But anyways, there are areas where wind is usually very high. For example, in the coastal region, in the coastal areas, you can have a lot of wind turbines. And because this is green energy, so it is at least better than the nuclear powered power plants and the steam or coal based power plants. They are better in terms of the environmental effects. So go through the text that is there. It is also important to look into it. They have usually two types: horizontal axis wind turbines and vertical axis wind turbines. Please go through the text and it will be understandable. But anyways, this is not part of our scheme of studies. These are different shapes of the wind turbines. There are even moving airfoils where you can move it from one place to another place depending upon what area is receiving more wind, and then we can install them. Turbine specific speed is also an important part. This CP and CH, basically we use these terms, they are coming from the pumps. So it will be clear when we are next week or 2 weeks from now when we are entering the pump section. So this is coefficient of the power and coefficient of head capacity of these things. So we'll look into it when we are studying the pump. So in the same way that there is pump specific speed, there is also turbine specific speed, and there is this relationship between the two. For the time being, just ignore these two slides and then we'll look into it when we study them in pumps. Also, this is the same thing related to that. Okay, so this is it for this lecture. We'll study few numericals in the next lecture related to the turbines, and then we'll move to the pumps, and this final 2 or 3 slides which are related to the specific speed and specific capacities and of the turbines and pumps. It will be clear when we go through the pump section. So until then, if there is anything, just drop the question on the LMS on the query thing, and I'll try to answer it as quickly as possible. Again, important is that you go through these sections that I mentioned. This is important to look into them. I'll be posting some an assignment. This time it would be a very simple assignment. So I'll upload it on the LMS, and also there would be a couple of numericals that I'll be uploading. So please go into them, go through them, and if there is any problem, anything, just drop an email or drop your query on the LMS section. Till then, see you in the next week, inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.